What is the math behind neural network activation functions? Imagine you're trying to teach a robot to recognize different shapes or understand language. To do this, it needs to process lots of information in a way that makes sense. That's where activation functions come into play. They are the secret sauce that helps neural networks learn complex patterns. But what exactly is the math behind these functions? Let's break it down in simple terms. At each neuron in a neural network, we start with a bunch of inputs. These inputs are multiplied by weights, which are numbers that tell the network how important each input is. Then, a bias is added to this sum to shift the result. Mathematically, it looks like this. The output of a neuron is the activation function applied to the weighted sum plus the bias. So, it's like this. Output equals the activation function of the sum of each input times its weight plus the bias. The main reason we use activation functions is to add non-linearity. Without them, no matter how many layers we add, the network would just behave like a simple line or a flat plane. It wouldn't be able to learn complex patterns. Activation functions turn the linear sum into something more flexible, allowing the network to model intricate data relationships. One common activation function is the sigmoid function. Its math formula is 1 divided by 1 plus the exponential of negative. It squashes any input into a value between 0 and 1. This makes it great for probability estimates or binary decisions. Another popular one is the hyperbolic tangent, or tan. Its formula involves exponential functions as well, but it maps inputs to a range between -1 and 1. Because it centers data around 0, it can help neural networks learn faster. Then there's the rectified linear unit, or ReLU. Its formula is simple. It returns 0 if the input is negative, and the input itself if it's positive. This straightforward function is very fast to compute and helps prevent the vanishing gradient problem, which can slow down learning. It's become the go-to activation function in many deep learning models. Some specialized networks use radial basis functions. These functions depend on the distance between the input and a center point. For example, a Gaussian radial basis function uses an exponential of the negative squared distance divided by twice the variance. This helps the network focus on local regions of data, which is useful in certain tasks like pattern recognition. Activation functions also help stabilize training by keeping inputs within manageable ranges. This makes the process of adjusting weights through gradient descent more reliable. When training models like ChatGPT or image generators like DALL-E and Midjourney, these functions enable the networks to learn from complex language and visual data. Understanding the math behind activation functions helps us see how neural networks become capable of learning such diverse and complicated tasks. They transform simple linear combinations into rich, nonlinear representations, which is essential for modern artificial intelligence.